Dear students, in this video I am going to discuss about uses of dihydrogen and different types of hydrides. First, you just know uses of dihydrogen. It is used in the manufacture of ammonia, banaspati ghee, methanol, HCl, etc. Dihydrogen used as reducing agent in metallurgical process. Liquid dihydrogen mixed with liquid oxygen and used as a rocket fuel. Okay, so liquid dihydrogen mixed with liquid oxygen is used as a rocket fuel in space research. Okay, it is also used in fuel cells for generating electrical energy. Okay, now this dihydrogen is used in the atomic hydrogen torch and oxyhydrogen torch, as they can produce high temperature. They are used for cutting and welding purposes. Okay, so it is used in the atomic hydrogen torch and oxyhydrogen torch for cutting and welding purposes. Okay, now I am going to discuss about hydrides. What is hydrides? Dihydrogen under appropriate reaction condition combines with almost all elements except noble gases to form binary compounds called hydrides. Okay, actually binary means this compound has two composition. Okay, so depending upon the behavior and nature of bonding of the hydrides, depending upon the behavior and nature of bonding, the hydrides can be classified into three main categories. What are they? First, ionic or saline or salt-like hydrides. Secondly, covalent or molecular hydride. And thirdly, metallic or interstitial hydride. One by one, I will discuss different types of hydrides. First, ionic or saline or salt-like hydrides. Okay, so these hydrides are formed when hydrogen combines with electropositive alkali metals or alkaline earth metals, that is with S block elements, and these S block element having electronegativity less than hydrogen. Okay, so these hydrides are formed when hydrogen combines with S block elements. Okay, example: lithium hydride, sodium hydride, calcium hydride, strontium hydride, etc. The formation of these ionic hydrides involves transfer of one electron from the metal atom to the hydrogen atom. One electron from metal atom to the hydrogen atom, and so these hydrides ion gets helium configuration, helium like configuration. Okay, and hydride means H minus. Okay, again you must remember that this H minus is soft enough to be strongly polarized by small ion like beryllium 2 plus and magnesium 2 plus ions. For this reason, beryllium hydride and magnesium hydride are significantly covalent. Barium hydride and magnesium hydride are significantly covalent. Their nature is not ionic, as H minus, that is hydride, is soft enough to be strongly polarized by the small cation like beryllium 2 plus and magnesium 2 plus ion. Okay, now see the preparation. Actually, these hydrides are prepared by heating the metal in an atmosphere of hydrogen under pressure over the temperature range 150 to 600 degrees Celsius. So these hydrides are prepared by heating the metal in an atmosphere of hydrogen under pressure over the temperature range 150 to 600 degrees Celsius. See one example: lithium combines with hydrogen at 600 degrees Celsius and form lithium hydride. Okay, now we see the thermal stability order of group 1 hydrides. Group 1 hydrides are lithium hydrides, sodium hydrides, potassium hydrides, rubidium hydrides. Okay. Now you must remember that H minus, that is hydride ion, is small in size. So it form good lattice with small size cation, as packing is will be good. So as H minus ion, hydride ion, is small in size, it form good lattice with small size cation. Okay. So H minus will be more H minus, that is hydride, will be more stable in case of lithium hydride. Then the thermal stability decrease down the group. So lithium hydride is more stable than sodium hydride, then potassium hydride, then rubidium hydride and cesium hydride. Okay. Now we see that this hydride in the molten state breaks into cation. Like if you see one example, calcium hydride in molten state, it form calcium 2 plus and H minus ion, and this ion conduct electricity with the liberation of hydrogen at the anode, with the liberation of hydrogen at the anode. And this liberation of hydrogen confirms the presence of hydride ion in them. This liberation of hydrogen ion confirms the presence of hydride ion in them. Okay. Now you must remember that lithium hydride do not decompose on strong heating, as H minus ion is very small in size and lithium also small in size. They occur a extremely good packing, and this lithium hydride is highly thermally stable, so they do not decompose on strong heating. Okay. Otherwise, except lithium hydride, they burn in air on strong heating due to their decomposition into hydrogen. Okay, which is inflammable. This hydrogen is inflammable, but lithium hydride do not decompose on heating. Okay. Now you must remember uses of ionic hydrides. These ionic hydrides act as good reducing agent in organic chemistry. This is used as reducing agent. Lithium aluminium hydride, lithium borohydride are made from ionic hydrides and they used as strong reducing agent. Okay. Lithium hydride form dimeric aluminium chloride from lithium aluminium hydride, and lithium hydride combines with diborane and form lithium borohydride. Okay. This is uses of ionic hydride. Okay. Now covalent or molecular hydrides. Very important, covalent or molecular hydride. When hydrogen combine with elements of comparatively high electronegativity, when hydrogen combines with elements of comparatively high electronegativity such as p block elements, covalent or molecular hydride are formed. So covalent or molecular hydride are formed by the combination of hydrogen with p block element. Okay. Now this covalent or molecular hydride can be further classified into three categories according to their relative number of electrons and bond present in their Lewis structure. They are based on the relative number of electrons and bonds present in their Lewis structure. What are the types? Electron deficient hydrides, electron precise hydrides, electron rich hydrides. So electron deficient hydrides. These hydrides have less number of electrons in the valence shell of the central atom. These hydrides have less number of electron in the valence shell of the central atom. Okay, usually less than 8 electron in the valence shell. So their monomer do not satisfy their usual octet rule. So their monomer do not satisfy the usual octet rule. The element of group 13 form this type of hydrides. Okay, the element of group 13 form this type of hydrides, which gain stability through the formation of dimers. This type of hydride gains stability through the formation of dimer. Okay, and you see that due to deficiency of electron, these hydrides act as Lewis acid. Okay, and as they are Lewis acid, they form complex with Lewis bases such as ammonia, hydride ion, etc. Okay, so electron deficient hydrides formed by the combine of hydride with group 13 element, and they form dimer to gain the stability, and as they are electron deficient species, they act as Lewis acid. Okay, and as they are Lewis acid, they combine to form complex with Lewis base. Okay, next, electron precise hydrides. These hydrides have exact number of electron in the valence shell of the central atom so as to write their conventional Lewis structure. It have exact number of electron to fulfill their octet rule. Okay. These type of hydrides are formed by group 14 elements. See the example: CH4, SiH4, GH4, gallium hydride, silicon hydride, germanium hydride. Okay. Now, electron rich hydrides. These electron rich hydrides have number of electron in the valence shell of the central atom so as to write their conventional Lewis structure. More number of electron than to write their conventional Lewis dot structure. The excess electrons are present in the form of lone pair. The excess electrons are present in the form of lone pair, such as in ammonia there are one lone pair, in H2O there are two lone pair in oxygen, in HCl there are three lone pair in chlorine, in H2S there are two lone pair in sulfur. Okay, so due to the presence of this lone pair of electrons, these hydrides act as Lewis base. Due to the presence of this lone pair, these hydrides act as Lewis base. Okay, and form complex with Lewis acid. Okay, see that B2H6, one Lewis acid, react with ammonia, that is a Lewis base, and form a complex. Okay, this is covalent or molecular hydride. Next, metallic or interstitial hydride. These hydrides are binary compounds of hydrogen and transition elements are generally formed when D block elements of group 3, 4, 5, 6 only for chromium, 10, 11, 12 and F block elements are subjected to react with dihydrogen at elevated temperature. So these metallic or interstitial hydride form by the combining of dihydrogen with D or F block element. But remember that for group 6 only chromium form metallic or interstitial hydride. For group 6 only for chromium form metallic or interstitial hydride. And remember that group 7 to 9, the metals of group 7, 8 and 9 do not form hydrides. The metals of group 7, 8 and 9 do not form hydrides, and the region of the periodic table for group 7 to 9 is called hydride gap. So, the region of periodic table from group 7 to 9 are called hydride gap as they do not form metallic or interstitial hydride. Now, why these are called interstitial hydride? Actually, hydrogen atom being small in size occupy the interstitial space of the metal lattice. Hydrogen atoms being small in size occupy the interstitial space of the metal lattice. So, it is known as interstitial hydrides. Okay. Now, see that the composition of interstitial or metallic hydride of some lanthanides and actinides belonging to A block may not correspond to simple whole number ratio, and therefore they are called non-stoichiometric hydrides. They do not correspond to simple whole number ratio. For this, they are known as non-stoichiometric hydride. See the example. Lanthanum hydride 2.87. This is not a whole number. Ytterbium hydride 2.55. Okay, so see the example. They are not whole number ratio. So they are called non-stoichiometric hydrides. Okay. Up to this is your today's lesson.